Hello, thank you for joining today's webinar where we will talk about linear and nonlinear buckling. So before we start, as always, let me introduce myself. My name is Piotr Stępień. I'm CAE engineer and I'm working in Midas IT company in the Midas NFX technical support department. So today's session will be based on examples mostly, and I will present to you as well some small theoretical introduction to linear buckling analysis, but we will be focused on the examples, as I said. We will not talk about mathematical and numerical methods too much, and we will simply go through simple examples, and we will focus how to create buckling model for static analysis, for example, how to prepare model for nonlinear analysis, and why analysis, let's say nonlinear analysis is better than linear for this type of problems. And I will show you as well how to add imperfection to the model using Midas NFX. So I hope everything is fine with the sound. So at the chat section you can put your questions during the webinar, so please let me know if the sound is fine. I will appreciate that very much. So at the end of today's presentation, as always, there will be some time for the questions. So you can use this chat section to put them, and we will back to them, let's say, later. Okay, so let's start the presentation, and we are starting from the definition of the buckling. So as we see, the buckling is defined as instability of equilibrium in structures that occurs from compressive loads or stresses. And as it has been written on the slide, a structure or its components may fail due to buckling at loads that are much more smaller than those that produce material strength failure. And buckling often stands for the catastrophic failure, and most of the structures are designed to prevent this phenomena. But not every kind of structure. So one of the exceptions can be, for example, column behind the steering wheel. So we see this example on the picture A. And this column is designed to fail, which means it is meant to buckle during a car crash, for example, to prevent impaling the driver. But in contrast, the columns of the building are designed so that they don't buckle under the weight of the building. And buckling is commonly understand as is instability of columns under compression, and any axial members that support compressive axial loads are called columns, but not all structural members behave the same. So if a compressive axial force is applied, for example, to a long strip, then it bends significantly. So we can observe this response to the picture C. If the columns of the building were to bend in the same way, the building itself would collapse. And when the columns buckles, the collapse is usually sudden and catastrophic. So there are several questions that we are always asking ourselves. So some of them sounds like that. Under what conditions will a compressive axial force produce only axial contraction, and when does it produce bending? This is the first question. When is the bending caused by axial loads catastrophic? How do we design to prevent catastrophic failure from axial loads? Finally, we are looking for the influence of the geometry, materials, boundary conditions, and imperfections, and we will talk a little bit about these problems. So some of you usually asking me something, so I received first comment. So one of the listeners is talking about the aircraft structures, and they are also subjected to the, let's say, buckled loads. Okay, but we can back to these comments later. So usually these are the questions that we are looking for the answer. So this presentation, let's start from the small introduction to linear buckling. And as I said, I will not talk too much about complex mathematics today, but using this simple example, I will try to explain how the linear buckling analysis works. So everything starts from the Euler buckling, which is the basic example for this phenomena, and it's very easy to explain using this. So as you see, this picture describes simple boundary problem for presented beam, and bending theory is used for buckling, let's say, description. So let me explain step by step what is needed to derive this buckling equation, which I hope you know and it's known by you. So let the bending deflection at any location x be given by Vx, function V of x, which is shown in the figure. So an imaginary cut is made at some location x, and the internal bending moment is drawn according to specified sign convection. So the internal axial force N will be equal to P. So by balancing the moment at the point A, we obtain a sum of m zeta plus P multiplied by V equals to 0. And substituting this moment curvature relationship of this equation, which governs this behavior, we obtain the differential equation 1a. So if buckling can occur about any axis and not just the zeta axis as we initially assumed, as I initially assumed on this picture, then of course these subscripts like zeta zeta in the area moment of inertia should be dropped. So this simple boundary value problem can be written using equation 1a and 1b. And for this equation, this symbol lambda means square root, which includes the force divided by Young modulus multiplied by moment or inertia. So this bending deflection will equal to, when it equals to 0, would satisfy the boundary value problem represented by those two equations, 2a and 2b. And this trivial solution represents purely axial deformation due to compressive axial forces. And our interest is to find the value of P that would cause bending. In other words, we are looking for non-trivial solution to the boundary value problem. So at this moment, let's take a look on the equation 1b once again. And the question is, does it look familiar? So I'm asking you this because actually it's very simple to guess that this is linear second order differential equation. And of course, we met each other, this equation during, for example, linear dynamics. And the general solution for the differential equation has been presented and at this line. So from this, let's say, from this first boundary condition to A, which has been presented on the previous slide, we can obtain equation 4, which is like this, sounds like this. So to satisfy this condition, for this first boundary condition, constant A is supposed to be 0, and simultaneously for the second boundary condition, this expression can be 0. And actually this expression, which consists of B constant sinus lambda multiplied by L, where L is the length of the beam. So this equation is called characteristic equation or the buckling equation. So, and this previous equation, which is called as characteristic equation, is satisfied if this lambda L equals to n P. And substituting this for lambda and solving for P, which is important, we can obtain this expression, which leads us to the critical force for the linear buckling. So for the lowest value of P, n should equal 1 in equation 7, for example. And furthermore, minimum value of I, which stands for the cross-sectional moment of inertia, should be used. And once again, the critical buckling load has been presented as equation number 8. So this is critical buckling load, and finally is also called Euler load, and buckling will occur about the axis that has minimum area moment of inertia. Equation number 9, which stands for the solution for the deflection, represents the buckled mode, or we can say eigenvectors, and we can notice that the constant B in the equation 9 is undeterminate. And this is very typical for the eigenvalue problems, and it looks very similar to the linear dynamics problems. So you can refer to our previous webinars and you will find some more information about that. So the importance of each buckled mode shape can be appreciated by examining figure below. So if buckled mode 1, this is what I'm showing you right now using the cursor, is prevented from occurring by installing a restraint or support, then the column would buckle at the next higher mode at critical load values that are higher than those for the lower modes. So point Y, for example, on the deflection curves describing the mode shapes that has got two attributes. For example, it is an inflection point and the magnitude of deflection at this point is 0. The same, the curvature at inflection point is 0, which means the internal moment and zeta at this point is 0. And if the roller supports are put at any points, so if we add some rollers at any points, any other points than the inflection points, of course the boundary value problem will be different, the eigenvalues will be different, and actually the solution will be different. Okay, so in equation 8, this I, which stands for the moment of inertia, can be replaced by expression area multiplied by r to the power of 2. So this A is the cross-sectional area and R is the minimum radius of duration. So right now I'm excuse me. Okay, so I will, at this moment I received some information that the audio is not clear, so can you provide me some feedback according to this? Because some of you told me that the sound is great, but I think, yeah, so it's good. Okay, thank you. Okay, so let's continue. So once again, let's back to the slides, and as I said, in the equation number 8, we can replace the moment of inertia by cross-sectional area multiplied by radius of duration. And right now I'm referring to the simple strength of the material definitions. So you can find all of this in the equations in the book. But let's say we can obtain right now what is different. This expression like L effective divided by R is defined, it defines as the slenderness ratio, and this is very important parameter. Okay, so what is important for this slide, this equation number 8 is applicable, let's say, only to simply supported columns. However, the process used to obtain the formula can be used for other types of supports. And this table shows the critical elements in the derivation process and the results for 3 other supports. And formula for critical load for all cases shown on the picture can be written as equation 10. And this is what I said, this L effective, it means effective length of the column, and the effective length for each case is given at the last row of the table. So in this equation number 8, as I said, this expression I can be replaced by the area divided multiplied by the radius of duration, and this expression stands for the slenderness ratio. And sigma, let's say critical, is compressive axial stress just before the column would buckle. And this equation is valid only in the elastic region, which is valid for the cases where sigma critical is less than sigma yield, for example. And we can use as, let's say, for example, as non-dimensional variables are used in the plots in the figure which has been presented. These plots can be used for the metric units because we are using the ratios, for example. And the slenderness ratio is defined using effective length, and due to that, these plots can be applicable to columns with different supports. If we take a look on this picture shows envelopes for steel, aluminum and wood. So the failure envelopes in figure show that as the slenderness ratio increases, the failure due to buckling will occur at stress values significantly lower than the yield stress. So additionally, I'm presenting three types of the columns because this is very important to distinguish which approach we have to use for the analysis. So not every type of column, if let's say if we are considering the buckling of the columns, are valid for the analysis. So let's start from the slender. So for this type of columns, the failure will be caused by elastic buckling. And as you see, there are some additional assumptions like pre-buckle deflections are small and the critical load is reached before the material yields. So intermediate column, the second, which is a combination of yielding and buckling, and the column number 3, which is short column, and this design is based on using yield stress as the failure stress. Okay. So right now, let's do some example. This example will be very simple, so I think everyone started FEA analysis for the buckling from this example. So what we will do, we will perform simple, quick calculation for the case presented on the slide. The Young modulus is 210 gigapascals. The length for the beam is to 3000 millimeters, and the cross-sectional dimensions are presented on the slide. So right now I'm switching to the software, and let's sketch it quickly, and let's provide some results. So right now I'm clicking on the line. I'm using 3D option, and I will sketch the geometry for the column. Now I'm hiding the grid, and I will display the local coordinate system. Material has been defined, so actually we are starting this example from the property definition. So I'm clicking on add. From the one-dimensional properties, because we will use this type of model, I'm clicking on the bar, and let's click on the section, and let's define the values for the cross-sectional parameters. So for the height, let it be 100 millimeters. For the width, it will be 50. Width for the flanges. The thickness for the web will equal to 4.5, and thickness for flanges will be 7. So we have it. So as you see, I'm using the I section, so I'm clicking on OK. The cross-sectional parameters has been calculated automatically, so I just simply click on OK. And I'm going to the mesh. I'm clicking 1D, and let's mesh this curve using 20 as the number for the divisions. So as you know, we have to add orientation for the beam elements. So I will change the orientation, and I'm clicking OK. And the curve has been meshed, so right now I'm clicking on the mesh and properties, so we can display this cross section. Okay, so let's add some constraints and let's solve this beam as the two-dimensional case. So I'm clicking on constraint. I'm adding support for the lower node, for the node at the bottom. Okay, so I'm clicking on fixed. I'm clicking apply, but actually, to be consistent with the model, it cannot be fixed, so please excuse me about that, because we have to go to the advanced option, and we have to leave this degree of freedom free, because it should be consistent with the initial model. So the rotation is free. Let's click on apply. Let's constrain the second, and for this moment, let's release the translation on zeta. So I'm clicking on OK, and right now we are able to add some buckling force. So I'm selecting this node again, and as the reference, let's apply the load -1 Newton. Why -1? Actually, I will explain you in a couple of seconds. So let's click on OK, and let's go to the analysis case, and let's set up the analysis. So let's expand this flyout menu. Let's check linear buckling. So as you see at this end subcase consists of linear static and eigenvalue, which is, as I said at the beginning of the presentation, software is performing eigenvalue analysis to provide you a result for the buckling. So let's click OK. For example, actually we can click on this eigenvalue, we can go to the subcase control, and for some difficult, let's say complex models, we can review the options, so we can define how many eigenvectors should be considered for the solution. We can also check the option for the checking of the nodes if it's needed. So at the moment I'm clicking OK, and I'm leaving these options, so I'm clicking OK. And let's calculate this very quickly. So as you see, the solution has been done in a couple of seconds. So the solution consists of two solutions actually. We have a solution for the linear static as an eigenvalue. So for the linear static, we can see the typical response as for the pure, let's say, compression state. But to see the deformation for the buckle, we have to investigate these modes, which stands for the buckling modes. And why it's convenient to assign load -1 as I did. The answer is very simple. So for the moment, I will switch to the presentation, and now you can observe the same results. So FEA results interpretation for the linear buckling analysis has been presented at this form. So critical load is proportional, equals to the proportionality factor, we can say, but this is eigenvalue multiplied by the actual loading. So it's very convenient to add -1, because then lambda will be always stands for the critical loading. So in that case, eigenvalue equals to 33,734 newtons, and we can compare this with the theoretical result, and we see it's very, very close. Okay. So actually we can back for the moment, and we can investigate the other shapes. So it was the first mode. Right now we are seeing the second mode, third mode. And what is important, the values are meaningless because we are solving the eigenvalue problem. So you have to remember that. Okay. So now let's switch again to the presentation, and let's start from the simple comparison of the linear and nonlinear analysis. And this is very important to understand the basic concepts, let's say, and I will provide you, which will provide us huge impact for the correct modeling. So generally speaking, in physics and other sciences, the question is, what is nonlinear system? So we can provide the general answer like that. In contrast to linear system, nonlinear system is that one which doesn't satisfy the superposition principle, meaning that the output of nonlinear system is not directly proportional to the input. This is very easy definition. So how this definition is related to the FEA? The best way is to look at the load displacement response of one or more characteristic load in introduction points. So if we take a look on the graph to the left, we see the structural response, which is deformation, and this deformation is linearly proportional to the magnitude of the load. And then due to that, we know that the analysis of such structure is known as linear analysis. And now let's take a look on the second picture. So when the load to response relationship is not linearly proportional, then the nonlinear analysis should be performed, and this means that the stiffness of the system will vary as function of the load, and obtained displacement can be very large, and changes in the geometry cannot be ignored. So generally speaking, there are three factors which are causing the nonlinear behavior. For example, in static analysis, I'm saying static because today we are talking about static response. So first cause of the nonlinearity is geometric nonlinearity, which we can observe, let's say, when the object is subjected to excessive deformation, or for example, load direction is changing. The second second reason is material nonlinearity, and this happens when the relationship between stress and strain isn't elastic. So, for example, nonlinear elastoplastic theory has to be used. And the third one is contact nonlinearity, and this is used to describe the interaction between the objects. For example, like that. Okay, so now let's talk about geometric nonlinearity, and I would like to say a few words which may be related to the following phrases like large strain, large rotation, large deformation. Buckling itself is related to this large rotation and deformation. So this geometrical nonlinearity behavior occurs when the changes in the geometry of the structure due to its displacement under load are taken into account in analyzing its behavior. So the change in geometry affects both equilibrium and kinematic relationships, for example, strain displacement. And in geometric nonlinearity, the equilibrium equations take into account the deformant shape, whereas in linear analysis, the equilibrium equations are always based on the original undeformed shape. So as the consequence of this, the strain displacement relationships may have to be redefined to take into account the current updated deformed shape. And in the same time, it should be emphasized that large and small displacements, strains or rotations are possible. Geometric nonlinearity doesn't always mean large displacement for that. So in many thin plane structures, for example, displacements of the order of the plate thickness will give rise to geometric nonlinearities. Geometrical nonlinearities affects as well the influence of acting loading. So in nonlinear analysis, which are considered large deformation, direction of the load is changing in function of the structural deformation, and in other words, this means that the applied forces can follow up the deformation. And most engineers associate this geometrical nonlinear problems with large displacements effects like buckling. But as I said, these problems can also involve small displacements. And let's say examples of the problems of this type of problems can be classified as follows. So what I would like to say, I would like to introduce to you difference, let's say, between the small strains for the geometrical nonlinear problems and large strains cases, because this is actually the biggest problem. So in case of small strains problems, they are associated with small or large rotations, and problems in which small rotations occur include struts, shells, arches deflected by transverse load, for example, clamped circular plates under transverse point loads, and some shallow spherical caps. Examples of large rotation problems include a fishing rod bent under the weight of the heavy fish. For example, this is the classical stationary helicopter blade hanging by its own weight, and buckling of Euler strut or imperfect Euler strut. They are examples of the small strains. And for the large strain problems, they are associated with the manufacturing processes like deep drawing, forging, rolling, extrusion. And this type of behavior leads for this type of behavior, it's important also to use material nonlinearity. So on the next slide, I'm showing to you the three phenomena which are associated with the geometrical nonlinearity. So as you see, they are called snapback, snap-through, and bifurcation behavior. Snap and this type of problems involving beams, plates, shells, where under the influence of external loads, the deformed shape of the structure may suddenly switch from one position to another. This is actually the most important thing. So what is the snap-through? The snap-through behavior usually occurs when there is a horizontal tangent in the load displacement curve at point which is called limit points, as shown in the figure, where the deformed shape suddenly jumps from one position to another, but the load remains constant. Snapback is very similar, but it occurs when there is a vertical tangent in the load displacement curve, where the load on the body suddenly drops, but the displacement remains constant, as it's shown on this figure. And bifurcation points, let's say bifurcation behavior, can occur on the load displacement curve as one or more solution paths that satisfy equilibrium intersect. In example, the solution can proceed along more than one path. So the deformed shape may be influenced by any initial imperfections or eccentricity on the applied loads. And buckling analysis is a special case of geometrical nonlinear analysis that deals with the equations of the type classified in the mathematics as eigenvalue problems. So for the linear problems, usually we are receiving this this value at this point, and we are not able to investigate what's happening after buckling. So it's not possible to analyze post-buckling behaviors. But if you are interested to learn this type of phenomena, and if you want to compare them or learn how to model them with FEA, MyDAS NFX has been equipped with these files which are ready to solve. So these NAFEMS files are included in our verification manual. So for those ones who downloaded our software, there is a path, and you can go there, you can open a PDF file, and you can perform yourself the study by yourself. Okay. So let's talk about linear buckling and nonlinear buckling, and let's do some assumptions to summarize. So let's say geometrical nonlinear buckling provides us a form of geometric nonlinearity, and for this type of problems, usually the deflections are not limited to small deflections. The stiffness of the structure is changing. Load paths may change, as I said, in these problems for the bifurcation. Follower forces may occur. I was talking about this as well. The structure may soften or harden, and several post-buckling phases may be met for the moment. So this linear and buckling analysis has got some limitations. So for example, we cannot, as I said before, we are not able to calculate or simulate real structure behavior because we cannot determine behavior after buckling. Material is supposed to elastic, so no plasticity or elastoplasticity behavior can be added, for example. In the same time, the nonlinear analysis provides some additional advantages. So first one is gives us possibility to calculate the real buckling load, and as I said, this nonlinear behavior can be considered. For the most of the problems related with nonlinear analysis, the solution has been performed, is being performed by Newton-Raphson method, and this method is actually really difficult to estimate structural behavior after buckling, and due to that, for the nonlinear buckling, especially for the post-buckling calculations, we are using the arc length method, or let's say displacement, and the second method, which based on the displacement control method, but actually the arc length is the method which is preferable. So as you know from the previous webinars, the Newton-Raphson technique provides incremental solution, but this method is very poor for the buckling problems because the slope at the limit points is exactly equal to 0. So which means the slope in this point will be horizontal, and simply it's not possible to converge. The same at this point, for example. So standard solution techniques lead to instability near the limit points, and it's not possible to catch the right solution for snap through and snap back points, and many of the problems simply fails. So as the solution, the arc length method has been developed. So this is also iterative technique, as we see on the slide, which is used to arrive at a reliable and accurate solution at, or let's say close to, limit points where the slope of the force displacement curve changes the sign. So it means, for example, in this point. So its main strategy is to advance the solution by suitable arc length measured along the load path itself. So therefore the solution is controlled by arc length increment rather than a load or displacement increment as previously. And in MIDAS NFX, this arc-length method can be set up from dialog boxes which are presented. So I will show you these dialog boxes for the next example. And we have three methods which are related to arc-length method. So I'm talking about the crease field, constraint types, rigs, and modified rigs. So all of the methods can be adopted by you for your simulations. And now let's back to the software, and let's do simple nonlinear calculation for the beam, and after that I will show you the procedure how to assign the imperfection, and let's say I will try to explain why we are doing this. So let's start from this case. So this time we are changing the environment. For the previous backlink calculation, our case was defined as 2D. Right now we will perform 3D case, and we will change the value of the force, and we will see what will happen for the Newton-Raphson result and for the angle length, for example. Actually, the solution has been provided. So for this type of problems, we see that Newton-Raphson can be not stable, but there are several reasons for that. So it's not only that Newton-Raphson is not stable itself, but there are other let's say causes for that, and other assumptions, especially because we are using simple beam which has got perfect shape, and the load has been applied let's say in the perfect way, is oriented perfectly normal to the cross section. So there are several reasons, but what is important to preview that for that case, Newton-Raphson may provide you some additional issues. So let's switch to the software, and let's set up the nonlinear model. So now I'm clicking on this log. I'm going to the static load, and I will edit the value, and let's provide this -43752 newtons. So you can actually provide any type of value. For this case, it will be fine. So I'm changing this. So for the moment, we have defined only axial loading. So I'm going to the analysis case. I'm clicking on the other, and let's add nonlinear static solution type, and let's set up the analysis controls. So first of all, I'm checking this geometry nonlinear button to be sure that we obtain the right deformation from the nonlinear analysis. Number of decrements will stay the same. If we click to this advanced nonlinear parameter, we will get the access to the arc length parameters. So for example, if you want to use this option, we can select the method, and we can set up the number of increments and the rest related parameters. So for example, we can use that. You can click OK, and let's click on OK, and we will see what will happen. So let's try to solve this problem like that. So actually what happened? It's easy to guess that the bar, or let's say beam, will not buckle. Why? Because there is a nonlinear analysis, and our bar is subjected to perfectly orientated load. So even if we display the results, even if we use some scale factor for the deformation, and if we play the animation, you will see that the rod responses as beam under compression, so which is actually not our goal. So to solve this problem, we supposed to add some kind of eccentricity, or let's say we have to model this eccentricity by some additional loads, or we can add some initial imperfection. But let's say this is the one-dimensional model, so for this presentation I will add let's say small moment. So I'm going to the static loads. I'm clicking on moment, and let's add some small moment which will act on zeta axis. For example, let's define 100 Newton or millimeters. We will see if it's enough. Okay. Oh, actually, excuse me, because I made mistake. But let's say just to be sure, maybe it will be much more convenient to back and use standard SI units. So I will switch Newton and meters, and I will go to edit. So let's this is moment on zeta, but it's supposed to be moment acts on x axis. So let's correct this, and let's click on OK. So we have a moment. Someone of you requested actually notice that there is a problem with the internet connection, so so don't be afraid, because this session is being recorded, so after the session we will put this on the YouTube channel, so you will get the access for that. So even if you have some problems, just you can skip it for the moment. Okay, so I added this moment, and the second step which is necessary to perform is to change a little bit the boundary conditions, because we are using the same model but in 3D case. So now I'm going to edit, and I'm clicking on the constraint at the bottom. So this is for the node at the bottom. I'm clicking on edit, and for this actually I want to keep this value, so rotation will be fine. Okay, so, and I want to release this rotation, so the only rotation around zeta axis, or let's say neutral axis of the beam, will be checked. Okay, and similar case for the second node. So for this moment, let's release, let's say, all of them, and then we will see what happens if our solution is fine. Okay, so let's perform this calculation. So let's solve it. So at this moment we obtain the solution for the arc length method, and if we go back to this bar, we are receiving the factor of the loading just before the unconvergence, let's say. So we can go to this nonlinear static, and we can see if the deformation is fine. So as we see, the shape right now, the backing shape, is very close to the shape that we predict from the linear static, from the linear backing analysis. And this happened because we added this this small moment. So right now the response is much more consistent with the linear static, but it doesn't mean that this is good in the same time. So just to check and verify the value, we receive the factor. So we apply the force our force value has been applied like 43,752. If we multiply this by 0.739, which is factor from the last increment, we should obtain the value very close with our eigenvalue result. So actually, the result has been provided there. So from the previous, let's say for the model presented, the value is a little bit different, but I simply made the model by myself. So from the beginning, let's say, and there is a small difference. So for the next model, actually, I would like to introduce to you a technique which is very helpful to add for the adding of the imperfection, and we will build a model of the cylinder. So on the slides you see the results for the linear buckling analysis. So we can observe the first eigenvalue, second eigenvalue, and third eigenvalue. And on the next slide I'm showing you the cases with the imperfections. So we will perform quickly the solution where there is no imperfection. So it's easy to guess that our cylinder, which is subjected to the compressive load at the top curve, will respond like a cylinder under compression, not like a cylinder under the buckling. So to avoid that, this initial imperfection is necessary, and we can use this technique for the analysis of the post buckling, let's say, cases. So how to do that in Midas and FEX? So let me switch to the software again, and now let's sketch the model very quickly. So I will use the geometry. The unit length, the unit of the length is meters, so 0.25 will be the radius. And let's extrude this curve on zeta. The length will be 0.5. Don't make solid, just make the cylinder. So we have the geometry. Right now let's mesh it. So I will use the mapped face, and the size will be defined like that, 0.0125. The property has been defined by me previously, so the thickness for the shell is 2 millimeters. And we are using aluminum alloy, and this is linear material in that case. So I'm clicking on OK. Let's click on preview, and let's click on OK. Let's hide all of the guiders, and let's assign the constraints. So I will fix all of the bottom nodes. So let's apply them. And let's add additional constraints for the top curve. So I will simply select all of the degrees of freedom except of the translation on zeta. We have that. And let's assign the force. I'm going to perform linear calculation first. So let's assign this -1, and let's divide this force by the number of the nodes, because I'm using the mesh directly. I'm not working on the geometry, so the geometry was useful only to create this mesh. but actually there are many techniques to do that. So let's click on OK, and the model is supposed to be ready. So now let's click on analysis case. Let's add linear backlink and let's solve the model. So in few seconds we will receive the solution. And this linear backlink analysis, excuse me, is commonly used to add the imperfections with the modes that we are expecting. So all the time it's very important to perform a backlink sensitivity study and to figure out which type of mode is important for your nonlinear study. At the moment I will show you how to add this imperfection from the result of the eigenvalue analysis, but in the same time you can, using this technique, you can provide your imperfections, let's say defined by yourself. So let's wait a couple of seconds for the result. That thickness has been defined by myself previously, so I prepared the model before this webinar, so I define material and property, so the thickness is provided in this card. So now I'm answering on the one of the question. So the thickness is related with the property, so you have to go to this card. Okay, so we have the results, and now we are able to investigate the modes. So we are actually received the compressive force. The value was -1, but it had been distributed on the nodes. So at this moment we have to multiply this force by this type of factor. So this is the first backlink shape, and as I said at the beginning, these backlink shapes results are meaningless in terms of the meters or stress values, but they are very important in terms of the nonlinear geometry study. So now I'm displaying the edges. So we have to find a way how to assign them for your nonlinear model, for example. So to do that, we have to use two models. So the procedure looks like following. It's very convenient to save your model with the second name, like for example cylinder 2. I'm saving this, and I'm opening the previous model because I need the data. So for that we have the results, and let's move it like that. Okay, so let's display these results again. So to assign the post-backlink, or let's say the imperfection, not post-backlink shape, but actually we can use this. We have to use Excel, Microsoft Excel, and the procedure looks like following. So basically we can go to, there are several forms, but I will show you the way which is actually the most difficult, but at the same time will provide you additional flexibility for the data management, let's say. So we have this analysis set, and as the result type we are using displacements, and for the moment we have to select the components of the eigenvalue analysis. So right now I'm of the displacement from the eigenvalue analysis. So now I'm selecting the translation on the X. I'm unselecting all of them. I'm selecting the first mode, which is presented on the screen. I'm selecting the node, and I'm simply selecting all of the nodes because I'm looking for the data for the geometrical position for all of this data. So I'm clicking on the node, and please remember this, that this is TY, which means translations on zeta direction. In other case we can call it delta X. So let's click on the table. So we see that, and here we have the result for the translation on the X. So right now we can simply copy this column and put this column, for example, in this place, the X. We can change the name. We are doing exactly the same procedure for the TY and TZ. So right now I'm not doing this, but I will show you the final result. So actually we are doing the same steps, but for the T2 and T3. And since we have it, we are going to mesh set, to the mesh tab, and there is an option which is called table. So using this option node, we are able to list all of the coordinates for our original model. And I'm selecting this map mesh, I'm clicking OK. I'm sorting this data respectively to the number of the node. And let's make a copy of these nodes. So Control C, let's put it there, and we have it. So basically we have initial coordinates, we have deltas, and the next step is very convenient to define some scaling factor just for the management. And the final result for the new coordinates, let's call it new coordinates, will be simply the sum of the x value plus delta. So it will be the same. And we are doing exactly the same procedure for the ty and tz with the respective component. And as I said, the scale factor is needed for the management of the response. So this is exactly what I meant, what I did in this first sheet in the Microsoft Excel. So these are the coordinates, these are the data. There is a scale factor, so I can, for example, change my new coordinates. For example, 1, it will be the same, but let's use 0.5. And let's make a copy, Control C. And for this model, I will use the model which has been prepared previously, because at this moment for the model, let's say, which I show you, for this cylinder, one or cylinder, I'm not sure if the number of the nodes are consistent, but let's say we can try with that model. So let's paste them, and we can see the result. So as you see, then the result is not so good, but let's say if we go to the model that I'm sure it's supposed to work, the result will be much better. And now you see why the scaling factor is important. So I'm using this. Let's sort it. And you see, now the nodes are much more consistent. So this is the backlink shape imperfection which comes from the eigenvalue analysis. Why it looks strange? It looks strange because, as I said, from the eigenvalue the displacements are meaningless, so we have to use the scaling factor to assign the imperfection correctly. So let's repeat this, for example, to this factor, and let's make a copy of the coordinates. Once again, Control C. Let's make a copy, and you see Right now, model looks much more better, and the imperfection is slightly visible. And this is how we are assigning these imperfections. So this is exactly the procedure. And using this technique, you can study the influence of the modes, and you can calculate your model. So right now, I prepared the calculation for the first eigenvalue. So we can, using the nonlinear analysis, we can investigate the backlink shape. So what is important? For this stage, which stands for the 0.4 total load, we still observing the first eigenvalue, but close to 0.5 after close 0.5, so 0.551 is the last increment where we are seeing the eigenvalue, and after that the structure starting to have some bubbles, and different path of stability is provided. So if we consider this 0.551, it means the backlink load for that is half less more, and this is very important. Okay. Okay, so actually you can use the same procedure to study other modes. So for the moment I will show you other results. So this is the result when I'm investigating the influence of the free modes. So the response is totally different. So from one side we can observe the bubbles, and from the second side the structure behaves still the same like for the first eigenvalue. Okay. So actually that's all. So in the same time, Midas NFX provides you opportunity to define the plasticity. So if there is a need to analyze this nonlinear material, you can provide your elastoplastic material using the stress strain or plastic hardening curve, and the model has been solved with the plasticity, so you can see the animation right now. So that's all for today. So I hope it was interesting for you and you are satisfied with technique. I skipped a few of the slides because actually the time has been exceeded for the current session. So if you have some questions or comments, please write this on the chat section. My email is piotr.stepian@midasit.com, so I will write to all of you. And use that you will be able to ask some questions. Video will be recorded and will be provided on the YouTube channel via the other service. PDF will be also provided, so you will be informed about this webinar soon. Okay, thank you for participating. Usually you will be informed by email, because I hope you provided your emails during the registration, so this is why we are asking for that, and we will send you. Okay, thank you so much. Have a nice day or have a nice evening, depending on the time zone, and see you soon. Bye bye.